Hello and welcome to Calc 1. We start off with 2.1, rates of change and tangent lines to curves. One of the first things we tackle in this section are the topics of average speed and instantaneous speed. And we start off with an example with the topic of freefall. For example, when a solid object is dropped from rest near the surface of the earth, it could be off of a cliff or a really steep mountain, and this object is allowed to fall freely. This object will have this motion of free fall, and in this equation we have here, we see that free fall is going to give us the distance fallen in feet after t seconds. So y would be the distance, and the t that's being squared here, that would be seconds. So this is for when we have feet. If we had y being measured in meters, alternative version would be y equals 4.9 t squared. So one thing we should note for distance, this is distance in feet, and then this distance is distance in meters. Okay. So we have this formula for average speed. Average speed over an interval t1 to t2 would be the distance traveled over elapsed time. Okay, you'll kind of notice that it looks similar to the slope formula, the old y2 minus y1 over x2 minus x1. Okay, just slightly different notation. Okay, so let's take a look at an example. A rock breaks loose from the top of a tall cliff. What is its average speed? A, during the first 2 seconds of fall, and B, during the 1 second interval between second 1 and second 2. So average speed. Okay, so let's figure out the average speed during the first 2 seconds of fall. So that means if we're using our formula, y equals 16 t squared, our time intervals are going to be between 0 and 2. So we're going to figure out what the distance fallen was at, well, at 0 would be nothing. And then we figure out what's happening at 2, and then we do the average speed formula. Okay, so average speed for this case we would do f of 2 minus f of 0 if you want to use function notation, over 2 minus 0. So if we had our function 16 t squared, let's plug in 2. So we have 16 2 squared minus 16 of 0 squared over 2 minus 0. Okay, and we can figure this out. 2 squared is 4, times 16 would be 64. 0 squared is 0, times 16 is 0. 2 minus 0 is 2. So we end up with 64 over 2, which becomes 32. So this will be 32 feet per second. Okay, let's take a look at the second part of that question. The average speed during the 1 second interval between second 1 and second 2. Okay, so for this part, we're going to calculate the distance fallen between 1 and 2. Right? So we would do 16 2 squared minus 16 times 1 squared over 2 minus 1. Okay, 16 times 2 squared, we did that, 64. 1 squared is 1 times 16 is 16, and 2 minus 1 is 1. So we have 64 minus 16, that would be 48 over 1, which is 48, so 48 feet per second. Okay, so any questions, just bring it up during class. Let's take a look at our next example. So in this one it says, find the speed of the falling rock in example 1 at t equals 1 and t equals 2 seconds. Okay, so the way we get that is if we take our average rate of change for our function, and as we get closer and closer to that second, that would give us our average rate of change. So we have this formula for that. As the amount of distance gets closer and closer to the point where we're looking at, for example t equals 1, that would give us the speed of the rock. Okay, it's going to be like an average speed, and we use it to figure out like a good approximation for instantaneous speed. Okay, we don't call it instantaneous speed because if it's instantaneous speed at that point, h would be 0, and we cannot divide by 0. Okay, but this is a good process to get us pretty close to instantaneous speed. Okay, so let's take a look at our example here. So we would first figure out, okay, we're going to do a time interval. Our time interval will be, in generic terms, will be t0 to t0 plus h. Okay, so what we're going to do then is figure, okay, if we're using this formula up here, x1 plus h, that would go into the first part. So now for us, this would be the t0 plus h. So we would do 16 t0 plus h squared minus 16 t0 squared. Okay, and then this would be divided by h. Okay, so let's see what this comes out to. For our purposes, because we're going to do t equals 1, we would do 1 here for our t0. Okay, that's going to act as our t0. So we would do 16 1 plus h squared minus 16 1 squared over h. Okay, now what we do with the 1 plus h, we're going to have to expand on that. So remember, we have to do 1 plus h times 1 plus h. 1 squared is 1 times 16 is 16. So you're going to do the FOIL on this first. You guys remember FOIL. First, outer, inner, last. Right? So when we do that, we would end up with 16. And then in here we have 1 plus h, that's plus 2h. plus h squared. Okay, so that's what happens there. Minus 16. We still have this over h. Okay, so if we distribute the 16, we end up with 16 plus 32h plus 16h squared minus 16 over h. Now one thing you guys will notice, the 16 and the minus 16, these will cancel. Right? Opposites, they cancel. Okay, and now so we're left with 32h plus 16h squared over h. Let's factor out an h from the top. So if we pull out an h, we have 32 plus 16h. And now we could cancel the h that we pulled out with the h from the bottom. So we're left with 32 plus 16h. So now remember we mentioned, or I mentioned earlier, that we want to see what happens as we get closer, as h gets closer and closer to 0. Right? So pretend you plugged in a 0 there for h. And notice what happens. You're left with 32. So this 32, this will be the speed, 32 feet per second. This will be the speed of the falling rock at t equals 1. (32 feet per second). Okay, let's try the same process for when t equals 2. Okay, almost identical. Okay, so when t equals 2, we would have 16, 2 plus t, 2 plus h I should say, minus 16, 2 squared over h. Okay, expand on the 2 plus h squared. So 2 plus h times 2 plus h, that would be 4 plus 4h plus h squared minus 2 squared is 4 times 16 is 64. And so we have 16 we will distribute to everything. So we have 64 plus 64h plus 16h squared minus 64. Okay, the 64 and the minus 64, they will cancel. So we're left with 64h plus 16h squared over h. Pull out an h from the top. So we have 64 plus 16h over h. Cancel out an h and an h from top and bottom. So that means we're left with 64 plus 16h. Okay, plug in a 0 for the h. As h gets closer and closer to 0, this term becomes closer and closer to 0. We are left with 64 to be the speed. So 64 feet per second would be the speed at t equals 2 seconds. Okay. Let's take a look at our next example. Example 3. Find the slope of the tangent line to the parabola y equals x squared at the point 2, 4 by analyzing the slopes of the secant lines through 2, 4. Write an equation for the tangent line to the parabola at this point. Okay. So the way we get the slope of the tangent line is we want to figure out first, we want to do the slope of the secant line. To get the slope of the secant line, we go through the process that we just did with the other problems. Okay, so to get secant line slope, this is going to be our delta y over delta x. Now our x value here is 2, right? So when we're looking at 2, 4, x is 2. So that means we're going to be plugging in 2 into our equation. Okay, but the initial process is the same because it's just an x squared. You'll see the first part to be 2 plus h squared minus 2 squared over h. Okay, so this gives us, if we expand this, this will be 4 plus 2h plus another 2h, that's 4h plus h squared minus 4 over h. H is cancelled, the 4's cancel, I should say. So we have 4h plus h squared over h. Pull out of h, so we have 4 plus h over h, cancel out the h's, so we're left with 4 plus h. Okay, so that means if we plug in a 0, right, we want the h to be as close to 0 as possible, our slope of the secant line in this case will be 4. Okay, so you can think of that as your slope. So m equals 4. Okay, so that's the slope. And then to write an equation for the tangent line to the parabola, well, now we could use point slope form because we already have a point. Right? We have the point 2, 4. So our point is 2, 4. This is like our x1 and our y1. And we have the point slope form, y minus y1 equals m times x minus x1. And so we could plug in y1, which is this 4. M is 4. X minus x1 is 2. We could distribute the 4. So we have 4x minus 8. Add 4. 4x. Negative 8 plus 4 will be negative 4. Okay, so then this would be the equation for the tangent line at 2, 4. Okay, let's take a look at another example. Figure 2.5, and here's the figure here, the graph on the bottom right, shows how a population of fruit flies, Drosophila, grew in a 50-day experiment. The number of flies was counted at regular intervals, and the counted values plotted with respect to the number of elapsed days and the points were joined by a smooth curve, the blue color curve. Find the average growth rate from day 23 to day 45. Okay, so to find the average growth rate, we're going to do average rate of change. Now they gave us the values here, so that's important. So at 23, we see that at 23 we have 150 fruit flies. At 45, day 45, we have 340 fruit flies. So we're going to calculate an average slope here. Okay, slope. So this is like our classic y2 minus y1 over x2 minus x1. Okay, so we would have 340. I'll do the y's first. 340 minus 150 over 45 minus 23. Okay, so 340 minus 150, that would be 190. And then 45 minus 23 would be 22. Okay, and then this would be, if we reduced it, 95 over 11. If you wanted to get a sense of that, divide it, use a calculator. 95 divided by 11, it would be approximately 8.6 flies per day. Okay, so that would be the average growth rate. Let's take a look at our next example. How fast was the number of flies in the population of example 4 growing on day 23? So on day 23, we examine and we see that we have a secant line here, right? And you could draw various secant lines. You see the other ones in gray. This one more or less matches the slope of that curve as you go from the bottom here. As you go up, you see how it kind of matches that slope. We're going to be using that. Now we picked a point up here to help us with that. 35 350 and the 23 150. And you can do this yourself as well. If you pick the point that's on the graph and use another point, it could be off the graph, that's fine, but as long as you match that slope, then you can calculate the average rate at that point. Okay, so notice down here we also have another point. This will help us as well. So we have 14 and 0, which is also off the graph. We'll use these 2 points to calculate our population increase. Okay. All right. So let's do a slope formula for this. We're going to have 350 minus 0 over 35 minus 14. One thing to note as you guys are calculating slope, keep it consistent. So if you do top y minus the bottom y, keep it the same way for the x's. Top x minus the bottom x. Okay. So we have 35 minus 14, that would be 21. And then if we did this on the calculator, 350 divided by 21, it would be approximately 16.7 flies per day. Okay, so any questions, just write me an email. I'll see you in class. Have a good day, and we'll see you soon.